There is an assumption built into modern engineering pipelines. Write a highly optimized prompt once, and it will scale seamlessly when you plug in a more capable backend model. But when an enterprise actually swaps out that underlying language model in a live production environment, the system often fractures. This specific, measurable degradation is formally defined as model drifting. It happens because vendors train and align their models using entirely different tokenization schemes, distinct reinforcement learning criteria, and custom role tags. A prompt tuned for one model's alignment space actively misfires in another. Operationally, this forces engineering teams into a costly loop of manually rewriting and revalidating their entire prompt library every time a vendor releases a new iteration. The paradox here is that transferring a highly engineered prompt from a source model directly to a target model frequently yields worse performance than if you simply used a prompt built natively for that new target. Prompt portability does not exist by default. Static strings of text cannot survive in a rapidly updating ecosystem without deliberate adaptation. This heat map shows cross-model prompt transfer performance on the human eval coding benchmark. The off-diagonal cells immediately reveal the extent of the drift across varying architectures. Look at what happens when a prompt optimized for GPT-5 is migrated to a Llama 3.1 70B target. The accuracy drops from 99.39% down to 68.70%. Yet, when Llama 3.1 uses its own natively optimized prompt, it achieves 79.47%. The transferred source prompt is actively bottlenecking the new model. We can calculate this as the transfer gap, the measurable shortfall between a transferred source prompt and the target model's true capability. The source variables inherently conflict with the target's behavioral distribution. This gap exists because prompts overfit to the highly specific latent space of the source model. They learn the exact formatting quirks and reasoning pathways that specific architecture prefers. Bypassing manual prompt tuning requires an automated translation layer that maps these quirks from one model to another. Resolving the transfer gap requires treating prompts as translatable code rather than fixed strings of text. The PromptBridge framework provides a training-free solution to eliminate this gap entirely. This architectural diagram shows the process beginning with a small, generic suite of alignment tasks fed into both the source and target models. These tasks run through a calibration engine, Model Adaptive Reflective Prompt Evolution, or MAP-RPE. In the first phase of this loop, a prompt generates a response that is rigorously evaluated by quantitative performance and behavioral metrics. In the second phase, a reflection model analyzes those metrics, identifies structural weaknesses, and proposes targeted refinements. To prevent the system from prematurely converging on a local optimum, it uses an island-based evolution mechanism. Isolated populations of prompts develop independently, exchanging occasional variants to maintain diversity. This evolutionary loop generates highly distinct, task-specific optimal prompts for both the source and target models. This calibration is entirely gradient-free. It modifies 0 internal model weights. The output of this stage is a precise pair of optimized prompts, perfectly mapped to the alignment tasks. MAP-RPE establishes the baseline ground truth of what optimal actually looks like for disparate architectures. Stage 2 bridges the newly calibrated prompt pairs. A mapping extractor module, powered by a high-capability LLM, analyzes the delta between the source and target prompts. This prompt template instructs the extractor to look for systematic, linguistic, stylistic, and formatting shifts between the models. The extractor generates a list of explicit structural rules and constraints based on those observations. Instead of relying on computationally heavy, gradient-based transfer methods, this approach uses direct linguistic summarization. These extracted rules capture the unique interface requirements and reasoning personality of the target model. The mapping extractor successfully distills opaque model alignment differences into an explicit, reusable translation lexicon. At test time, the framework applies this newly created lexicon to a completely new, unseen agentic workflow in a live production environment. We start with a source prompt designed for an unseen task. Notice that it completely bypasses the MAP-RPE calibration loop. The mapping rules are already established. It enters the test time prompt adaptation phase, meeting the abstracted knowledge. An adapter model immediately injects the distilled structural rules directly into the original prompt, effectively synthesizing a fully target-compatible version. This transformation occurs entirely in context. It requires 0 task-specific evaluation data to execute. PromptBridge achieves 0-shot prompt translation, bypassing the need for manual per-task engineering. We validate the framework's efficacy against traditional direct transfer methods using complex multi-agent benchmarks. This bar chart displays resolution rates on the SW bench verification set. Looking at a migration from an O4 mini source to an O3 target, the green PromptBridge bar reaches a 46.00% resolution rate. That represents a 27.39% relative performance improvement over the standard direct transfer baseline. On Terminal Bench, a benchmark assessing complex terminal environment tasks, the direct transfer accuracy of 33.75% jumps to 47.06% using PromptBridge. Destructural mapping holds across entirely different domains. The empirical data definitively validates the structural mapping approach across highly complex agentic environments. This raises a technical question. How do we know these prompt edits are adapting to the model and not simply overfitting to a specific task? The answer lies in the semantic delta. This chart maps the embedding shifts that occur during cross-model prompt translations. The consistently positive alignment across vastly different tasks proves that source-to-target migrations follow a shared, latent semantic trajectory. This suggests that source-to-target migrations are governed by stable semantic rules rather than heuristic guesses. Engineering teams must abandon static text instructions. In a rapidly evolving ecosystem, prompts are dynamic, compilable artifacts that automatically bridge the gap